Welcome to the first lecture in Unit 4. This is called Thank You, Prometheus. This is Prometheus, thief of light, giver of light, bound by the gods, must have been a book. There's a famous mythological story about Prometheus, who was the first person to give man knowledge in the form of fire. And there's a lot of people who think that this is kind of a symbol, that it's a symbol for books as opposed to fire itself. So let's take a look. The learning goals are that you will be able to differentiate between the ground state of an atom and the excited state of an atom. That you should be able to relate the quantized energy of light to the Bohr model of the atom. Remember the Bohr model of the atom from the previous unit. And that you'll understand the role of spectroscopy as an experimental tool. Now, you're not going to get into specifics of the various types of spectroscopy, but you need to understand how spectroscopy works. So this is what we already know. We already know that the atom consists of protons, neutrons, and electrons. And in fact, we said that the Bohr model of the atom is one in which you've got protons and neutrons in the nucleus, and that you had electrons at very specific, discrete energy levels that we called orbitals. Okay, so we also know that the electrons must be at defined energy levels, which are 1, 2, 3, 4. You can't have an electron at like 1.5. That doesn't work. Now, in the lab, we learned that different elements burn with different colors when exposed to the same flame. So if I take a standard natural gas flame and I put some different elements in there, they will change colors based on what that particular element is. Now, we also learned that the colors are consistent and unique for each element. So every time you burn sodium, it tends to be this orange color. Okay, and you get very, very, very different flames for each element. So now let's look at why. We already said that the electrons can exist at numerous energy levels, and that the state of an atom is determined by the energy level. So I can have, if this is a hydrogen atom, I could have a single electron right there in that first energy orbital. If I were to do that, that would be the normal state of an atom. Okay, but this electron can actually move up to the next orbital, or the next orbital, or the next orbital, and that's what we're going to look at now. The lowest energy state of a particular atom is when it's called the ground state. All of the electrons are as close to the nucleus as they can possibly be, because remember, opposites attract. The electrons want to be as close as they can to the nucleus. So if here's my nucleus right here, this electron right here is as close to the nucleus as it can possibly be and be in an orbital. Because of that, we say that it's in its lowest energy state. It's called the ground state. Now, the Offball Principle helps us figure out what is the lowest particular state for an energy level. Now, this is an introduction to the Offball Principle. Later, we'll learn a little bit more details about the Offball Principle, but for now, it basically says that electrons will fill in the following order. In the first energy level, so here's my nucleus, in the first energy level, I can put in 2 electrons. And that makes sense because if you were to look at the first row of the periodic table, there's only 2 boxes. There's one for hydrogen and there's one for helium, which means 2 electrons. Now in the second energy level, I can actually add 8 electrons. It's a little bit bigger, so I can go 2, 4, 6. I can put 8 electrons in there. And that makes sense because in the second row, you have 8 elements. And you see that pattern consistently all the way through. Now I can fill in 2 in the first energy level, 8 in the second, 18 in the third, and 32 in the fourth. We're not going to go past the fourth energy level at this point. Now, whenever the electrons are not in what's called the ground state or the lowest state, they're in what we call the excited state. Okay, a lot of times you will see the excited state referenced with the little asterisk or star at the top right corner of the element. What that's just basically saying is that I have a hydrogen atom, but the electron is not where it's supposed to be. It's a little higher level. It doesn't mean it's an ion. It still has an electron. It actually just means that it's a higher level energy electron. Now, in order for the energy to move to a higher energy state, the law of conservation of energy says that energy has to come from somewhere. So generally speaking, you can either heat it up or you can collide light with it or something along those lines, and it actually makes the electron jump from one level to the next. So electron excitation. So energy is always conserved like we talked about before. Electrons move up in energy when an atom absorbs energy. Okay, common examples that you see, electromagnetic radiation, so that's things like light, ultraviolet radiation, X-rays, could be infrared, those sorts of things. Collisions, 2 molecules that collide together and transfer energy. And then the other one, the one that we saw in this particular lab that we did, was heat, whenever it was exposed to a flame. Now, developing A1, it says draw the atomic model for the following states of helium. So what you see here is you see a helium atom, and we know that we have 2 protons, and we're going to say 2 neutrons as well in the nucleus. So there's my nucleus. Now for a helium atom in its ground state, helium is supposed to have 2 electrons. Now those 2 electrons should be in the ground state. They should be 2 in that first energy orbital level. Now this right here indicates that it's not in the ground state. So I still have 2 electrons, but instead of them being in the first energy level, I have to put at least 1. This is going to represent my nucleus, all of that. I'm going to have the first energy level and the second energy level. Now I have no idea of knowing exactly if it's in the second energy level, the third energy level, the fourth energy level, but what I'm going to do is I'm just going to take a pick. I'm going to say that I have 1 electron in the first energy level, but because it's in the excited state, I can't have the second energy or electron be in that same energy level because it's in the excited state. So what I'm going to do is I'm going to put it in the second energy level. It could be in the third, it could be in the fourth, it could be in the fifth. Both electrons could be in the second or third or fourth or fifth. It's up to you, but both of these would be considered to be correct. In other words, I have electrons in the ground state and electrons not in the ground state. Nexus is using Coulomb's law and effective nuclear charge. Explain why atoms always seek to be in their ground state. So remember, Coulomb's law just says that opposites attract. So you have a negative and a positive. Whenever something is not in the ground state, you have this positive and negative attraction between the two. So you look at that and you say, well, there's a positive and a negative attraction here. Why don't they just attract further? Remember, the electron has to be in an orbit. There is no orbit in between, so it can't move closer. But if you were to look here, there's an attraction between these two, and because it can move closer, it will move closer. So atoms will always seek to be in their ground state. Now, in the mastery level question, it says, burning hydrogen in a flame produces a series of colors shown below. This is actually the hydrogen emission spectrum. Now, design an experimental method to produce only red light. Now, if you know anything about light, you should realize that a red fire is actually pretty low in temperature. And a purple fire is very, very high in temperature. So a way that I would set up an experimental method to produce only red light is I want to produce only small orbital transitions. In other words, I don't want to go from the fifth energy level to the first energy level. That would produce things like violet. I want it to be a very, very small energy transition, like from 5 to 4. So to do that, what I want to do is I'd want my flame, or whatever I'm using to excite the electron, to be very, very low. So I would have a controlled, low temperature flame. Okay? Flames are very hard to control the temperature of to an exact degree. But instead, you can actually use something like a battery. If you have the right battery set up, the battery can actually provide energy to the gas as well. Except instead of providing a high voltage like we did in the engage activity, you can actually provide a low voltage, which would produce a very, very, very small transition. So far we've talked primarily about light, but really what we need to talk about is electromagnetic radiation. Electromagnetic radiation is what is produced as the electron moves from an excited state to a ground state. And you see that in the picture here. You see an electron moving from an excited state back to a ground state. So remember, the law of conservation of energy says that energy has to be conserved. So since I'm lowering the energy of the electron, I actually have to let out some energy, and I do that in the form of electromagnetic radiation. And because of that, the electromagnetic radiation can only have the same energy as the difference between these levels. So if the difference between these two levels is 2, the only type of electromagnetic radiation I can have is produced from here to here is 2. Now, if I have a third level right here, and the difference between these two is 1, well, then I could produce a transition from here to here, which would be 1, here to here, which would be 2, or overall here to here, which would be 3. So there's a lot of different electromagnetic radiations that can be produced depending on the specifics of your particular atom. But because of the way the atoms are situated, each atom has a different distance between these orbital structures because of Coulomb's law and effective nuclear charge. So the distance is going to be unique for each atom, and because the distance is unique, the energy is unique. Because the energy is unique, the color for each atom is unique. And you see that in the formula that we have here. This is the energy of radiation equation, and it can be calculated using this formula below. E stands for the energy. Energy is measured in joules, and the definition that we're going to use for energy is a measure of an object's ability to interact or to use. In physics, you'll use it to do work, but we're going to measure it as a measure of an object's ability to interact. This H term right here is a constant. It will never change. In fact, the term is Planck's constant, which you see right here. Now, it's got some goofy units. The reason for that, the units to be like that, is so that it cancels out and gives us energy later whenever you multiply the two things together. Now, you also see right here, this F stands for frequency, which is the last one in the table. You do need to know that in some books, some textbooks, some formula charts, instead of having frequency as an F, they actually write it as a V. I think that's somewhat confusing, so I will use the term F, but if you ever see it on a UT Quest or something where it says E equals HV, you know where that comes from. Now, developing B1. It says which chemical properties would produce the most unique, or which chemical period would produce the most unique frequencies of radiation. Now, remember, we said that the periods that are lined up along here represent the number of energy levels. So you could say the first energy level, like hydrogen, has a single energy level. Now, we know that's not a single energy level. We know there's actually more, okay? But it has one standard one. If you look here, this one has 7 standard orbitals. Because of that, there is much more room to transition between the orbitals than there are when there's only one. So we would say the chemical period with the most number of orbitals would produce the most frequencies of radiation, and that would be in the 7th period. Proficient level question. It says, what is the total energy that is of 1,500 yellow photons if the wavelength of yellow photons is 5.17 times 10 to the 14th hertz? So we need to use our equation E equals HF. So we look and we assign our variables. I look right here and I say 1,500. Well, I don't remember a number being anywhere in this equation. That's okay, we're going to come to that in just a second. I do know that whenever I use this equation, I know that H is a Planck's constant, which is 6.626 times 10 to the minus 34th. And in this case, it tells me the frequency. The frequency is 5.17 times 10 to the 14th. So I have enough information to solve for the energy, but what I need to realize is this equation right here represents the energy of a single photon, or a single part of radiation. Now, I don't have a single photon. I don't have a single thing of yellow light. Instead, I have 1,500. So if this represents the energy of a single photon, what I would need to do is multiply that by the number of photons in order to get the total energy. So you can think of it like this. E total is equal to NHF, where this N represents the number of photons, which in our case is 1,500. You plug it in, you would say 1,500 times 6.626 times 10 to the negative 34th times this frequency value, which it looks like I'm running out of room to write, but it would go right there. And you would multiply that out in your calculator. When you do multiply it out in your calculator, you would say 5.14 times 10 to the minus 16th, that's 10, joules. And you may look at that and say, wow, that's a really low energy because it's something times 10 to the minus 16th, and you're right. It's only 1,500 yellow photons. Realize that whenever you turn on a light bulb, it's letting trillions and trillions and trillions of photons out every second. The next one, the mastery level question, it says how many red photons would it take to equal the energy of 10,000 violet photons? So now, once again, we're looking at the equation E equals HF. But because I'm talking about a number of photons, I'm actually going to have to use the equation E total is equal to NHF. Now, in this situation, it says how many red photons would it take to equal the energy of 10,000 violet photons. So what I want is I want the energy total of the red to equal the energy total of the violet. Now generally you can't do this because all red light doesn't equal all violet light, but it's saying specifically, I want to know the red light that equals the violet light. So now I would plug in the equation NHF equals NHF. Now I separated it like this so you can see the red side and the purple side, because a lot of people will look at this and say, hey, everything cancels. You've got NHF. No, remember, N is going to represent red photons. Purple is going to represent, you know, this frequency right here, and there's going to be a different number as well. Now, the one thing that does cancel out on both sides is actually the H term. The H term is going to cancel out because you're going to have the constant on both sides. So now you can start to plug in your numbers. I don't know how many red photons I'm going to take, but I do know the frequency of those photons is this. Okay? I do know the number of violet photons, and a lot of people will get stuck here because they look at this and say 430 nanometers. Okay, 430 nanometers is not the correct answer in this particular case. 430 nanometers represents what's called the wavelength. Now, you should be familiar with wavelength already from middle school, but you can convert back and forth between wavelength using the equation C equals lambda F. Now, we will reference this equation a bit later, but C stands for the speed of light, which is 3 times 10 to the 8th. Wavelength, which I know is 430 nanometers, which means it's times 10 to the minus 9th, and then I can solve for the frequency. When you do that, you get a total frequency of 7 times 10 to the 14th. Okay? So at that point, 7 times 10 to the 14th, and it actually gives you this number in your notes. I didn't give it to me because I wanted to show you this particular formula, but it does give you that it's 7 times 10 to the 14th in your notes. So once you have this number right here, you can go ahead and solve for n. I would solve for n by dividing both sides by 4 times 10 to the 14th. Okay, whenever I do that, you can make your life much simpler if you look and say 7 times 10 to the 14th divided by 4 times 10 to the 14th. Those 10 to the 14ths cancel out. Now you can put it in your calculator and you can say, hey, it's about 17,500 photons of red light. Red light. Now we get into the concept of spectroscopy. Now, spectroscopy is a division of chemistry and physics, and it is a crucial tool that we have now to measure many different things. A lot of the information we know about what molecules are, how to manipulate them, and what we can get from them results from spectroscopy. Now, what spectroscopy is it's the study of the interaction between light and matter. Now, we've already said if you send light at a certain frequency, that light will actually cause an electron to move up, electron to move down, and so forth. So we have spectroscopy that is generally called spectrometers or spectrophotometers that can actually measure the frequency that's absorbed or measure the frequency that is emitted, and it can tell us something about the atoms. Now, the first type of absorption is called, spectroscopy is called absorption spectroscopy. And basically what you do is you have a sample. It's a sample material that you don't really know what it is, and you send all colors of light at a particular sample. And then what you have behind is you have a detector. And the detector should get all colors of light on the other side. The problem is that most of the time it doesn't, because when you send all colors of light, sometimes you're going to have just the right frequency that will allow an electron to jump from one level to the next. Okay? Not all colors of light will be able to do that, but some of them will. So what you're doing is you're going to measure what's called the missing light. So you're going to have the whole spectrum from red to violet, and then it's going to be all colored in, except for the fact that you're going to have a gap right here. And you're going to say, I'm missing light right there. And you're going to have all colors, and then you're going to say, I have a gap right there between here. So these are my two gaps. Well, those are the colors that have been absorbed. And if I know anything about that particular light, I can say, now this is the energy difference between these two levels. So you can actually find out quite a bit of information by what light is missing. Okay, there's a second type of spectroscopy that's very similar. It's called emission spectroscopy. And basically what you're doing is you energize the sample. So in this case, you're providing some sort of heat or electricity or something like that to take the atom or take the electron, and you're exciting the electron to the next level. So here's the electron. It's somewhere that it's not supposed to be. Then what you do is, as the atom is not happy that way, it will fall back down. Well, whenever it falls back down, it emits a color of light. And you can have a detector that measures that color of light, and then you can tell a little bit more information about what's there as well. Now, absorption and emission spectroscopy together can actually allow you to tell how much of something is in a solution. And we'll talk about that when we talk about solutions. Okay, you can use spectroscopy to identify elements. Now, if you were to look at this, this is unknown samples can be determined by comparing to known spectra. Here are my known spectra. I know that these spectra are unique for each particular element, so what I want to do is I want to figure out if an element is present. So if you look, I can say this right here, there's an orange and an orange. Okay, let me switch colors so we can see a little easier. This is an orange and this is an orange. Okay, that indicates that lithium is probably present in the sample. But for lithium to be present, all the colors that are here have to be present in the unknown. So I look at the next line. Yellow, yellow, it matches up. Green, 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 blue, 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 blue. All of the samples of lithium are present in the unknown spectrum. So what I know is that in the unknown spectrum there is lithium. Now I go through this for all the other elements to see if there's another element that's present, because if you look at here, there are more lines in the unknown than there are in here. So I go down to cesium. Cesium I can rule off the bat because you see how there's a purple line right here? There's not a purple line here. So I know that cesium is not present in the sample. I go to potassium. I say, well, it looks like that line lines up. That line lines up. That one lines up. That one lines up. You've got this triple line right here that you've got right there. So I would say that potassium is present in the sample. Okay, now we go to sodium. And if you look at sodium, sodium's kind of tricky. I would say that sodium is probably present in the sample because of this thick yellow line right here. And it looks like the second yellow line is kind of covered up by this green line, like they're kind of merged together. So I would say that sodium is present in the sample. And then I would also say that rubidium is present in the sample because all of its lines are there. Okay, in order for a sample to be there, all of the lines must match up. You can't have a missing line. So we say, does an emission spectrometer transition an atom from the ground state to the excited state? So how does it do that? So it does that by providing some sort of energy. Okay, now that energy can come in many forms. It can come from electricity, it can come from heat, and it can come from collisions. Now the most common form in this class is heat. The most able to be controlled is electricity. Electricity is the one where you can tap down the voltage a little bit, tap the voltage up just a little bit. Collisions are notoriously difficult to control, but they also provide, sometimes they're a little bit easier depending on the experiment that you're doing, but it's very, very hard to set up an experiment that way. Finally, it says, what element is present in the unknown sample? So we have an unknown sample right here. And then we're trying to figure out which one of these samples is here. Now, they're different sizes. Okay, sometimes a computer prints it out a little bit differently. So I'm not going to look and say, okay, well, it matches up perfectly. I've got to look at the numbers. And if you look right here, I have 477. 477 represents the nanometers. That is present in this sample. Okay, this one has 493, 493, 438, 438, or excuse me, 538, 538. Okay. This one has 575, but this doesn't. That's okay, because I want all the numbers of carbon to be in the unknown sample. Carbon's got 600, 658, and 712. So I can say with definity that carbon is in the unknown sample. So now I look at the next one, and it says iron, and it's got 392. Iron is not in this sample, so I can say that iron is not in this particular sample.